Okay, here's another example. Here's another type of question I could ask you. Find a plane perpendicular to these two planes, one with equation x plus 3y plus 2z is equal to 5. The second with equation negative x plus z is equal to 7. So how do we find a plane perpendicular to these two planes? Well, let's think about normal vectors here. So this first plane, we should be able to read off here that it has normal vector 1, 3, 2. We can just read this off. And then the second plane has normal vector n2 is coefficient x is 1. The coefficient y here is 0. Coefficient z here is 1. So n1 is a vector that is perpendicular, that's orthogonal to our first plane. n2 is a vector that is perpendicular, that's orthogonal to our second plane. And so we want our plane to be perpendicular to both of these. We want our plane to contain or be parallel to both of these vectors here. So we want 1, 3, 2 to lie in our plane, to be parallel with our plane. We want negative 1, 0, 1 to be parallel to our plane. How to find n3, a normal vector for our plane. How do we find something that's orthogonal to both of these vectors? We take the cross product of these two vectors. So what we're going to do now is let's crunch this out. Let's find the cross product of these two vectors, I hat, j hat, k hat, 1, 3, 2, negative 1, 0, 1. Okay, so this would be I hat times 3 times 1 minus 2 times 0. Minus j hat times 1 times 1 minus 2 times negative 1 plus k hat times 1 times 0 minus 3 times negative 1. This crunches out as 3i hat. 3i hat minus, okay, let's see here, 1 minus, so this would be 2, 1 minus 2 is negative 1 here. Times, 1 plus 2 is 3, negative 3 j hat, and this would be plus 3 k hat here. So our normal vector is 3, negative 3, 3. Real quick, it can be good to do a sanity check. Is this orthogonal to both of these? Well, we do n3 dot product n2. 3 times negative 1 is negative 3 plus 0 plus 3. That gives us 0. n3 dot product n1. 3 minus 9 plus 6 is also going to be 0. So that is reassuring to us. Okay, so we found a plane that is perpendicular. We found a normal vector. We found a vector that's orthogonal to each of our planes' normal vectors here. And as a result, we can quickly write down an equation of a plane. 3x minus 3y plus 3z is equal to 0. This works. You could change, this plane's normal vector 3, negative 3, 3. You could change the 0 to any other scalar you wanted. 3x minus 3y plus 3z is equal to 70 million. Also works. You can also, if you wanted to divide out by 3 here, this would also work. Nothing wrong with this. Okay, so this is one way that I can express this kind of problem. An alternative form of the previous question, find a vector parallel with these two planes where, those two are the exact same planes. Well, we we already did that. If our n3 here, 3i minus 3j plus 3k, if that's going to be perpendicular to, if this plane, sorry, this vector is perpendicular to the normal vector for the first plane, it's parallel to the plane. If this vector is orthogonal to the thing that's orthogonal to the second plane, it's also parallel with the plane. And so all we have to do is just use our n3 from the previous slide, 3i minus 3j plus 3k. So take the cross product of the normal vectors, that gives you something parallel to, to the intersection. Let me stick in that word there. So the picture is kind of like, let me color code here. Here is like the plane 3x plus 2y, 3x plus, x plus 3y plus 2z is equal to 5. Here is a, second plane here, negative x plus z is equal to 7. There is some line of intersection that they have here that's parallel to it. Okay, let's end here. Here's a pre-class problem. I meant to put this one earlier, but find the intersection of the line r of t is 1, 1, 0 plus t times 0, 2, 4, and the plane x plus y plus z is equal to 14. So refer back to your notes in the previous video if you need help on figuring out how to do this.